Hey guys, these are the notes for 2.3 day 2. A couple things to keep in mind. Excuse me, I'm not feeling very well. Sorry, gross. Anyway, you will be having a quiz tomorrow on 2.1 to 2.3. You can use your notes and you can also use a calculator, so you should bring both of those with you to class tomorrow. Homework for 2.3 is not due till Thursday, and I won't give you any more homework tomorrow. So we're going to start off right here. We're going to be taking what's called higher order derivatives, which basically just means derivatives of derivatives. So, which I have written right here. We're going to do first, second, third, and you're going to see the notation for all of them. But first of all, there's a couple ways. You know, we've talked about how the derivative, if it says y equals, we can call it y prime for the first derivative. Or sometimes we say dy dx, the derivative of y with respect to x. Sometimes when it's in f of x equals notation, we've been using f prime of x. It's also, you can say, the derivative of f of x with respect to x. And then the one we haven't used very much is this capital dx, and then you put y or f of x in here. But remember, all of those just mean the same thing. Find the derivative, or graphically find the slope of the tangent line. Or with our position functions, remember the first derivative was the velocity, or the rate of change, instantaneous rate of change. Well, the second derivative, no real surprise, you just do y double prime. If you're using this kind of notation for a second derivative, it looks like d2, which is tempting to think d squared. That's really not what it is. This just means take a second derivative. And with f of x, it's what you would think. It's f double prime. And same with this notation. It's just like the dy dx notation. So it looks like this. And last of all, if you see this notation, which we haven't seen very often, that's the second derivative. And I'll take it one more step down, but you could take this on out to infinity. A triple derivative would have 3 primes. It would have a 3 right here. So really when you see this notation right here, you just have to say, oh, okay, I need to derive it 3 times. Or you might see f triple prime. Or in this notation, it would look like this. That one you're not going to see a whole lot either, but I like to give fair representation to all of these, just in case. You never know what might pop up on the AP test. So any one of these means take a higher order derivative. And again, if you were doing the nth derivative, you would have n of those primes there. So the fifth one would look like this, etc. I don't really need to talk about that anymore. Down on the bottom here, let me move it on down. Uh-oh, what did I just do? I just messed it up. That's okay. Down on the bottom, if I can get my page, if you were asked to find all the derivatives, we'll get started. But this is set up perfectly for your power rule. So we would say the first derivative is 7 times 3 is 21, x to the knock it down a degree. And again, this is just straight power rule, minus 28, x to the third, and the derivative of a constant is 0. My next order derivative would be the second one, which we call y double prime, and I would just power rule it again. And I'd say 126x to the fifth minus 84 x to the second. And I could carry this on forever. I'll carry it one more time down. The triple derivative, I'd multiply. 5 times 126 is about 630. And I'd drop it down another degree. And then I'd have a 168x. And I could continue that. Kind of important to notice that every time you take a derivative, you're bumping that polynomial function down a degree, which was very clear when we were graphing. If you remember when we were taking the derivative of cubics, they went to parabolas or quadratics. When we were taking the derivative of our quadratics or x squareds, they went to lines. And when we were taking the derivative of a line, it went to a constant. And so they all get knocked down a degree with your higher order derivatives. The reason we use these is because it's a relationship in our position velocity situation. And right now we're going to have acceleration. And those of you who are in physics know that kind of when you do acceleration, it's if you're in feet per second, your feet is your position, feet per second is your velocity, and feet per second is your acceleration. And every time you say that word per, you're doing another rate of change. Or calculus-wise, you're doing another derivative. So it's probably not going to be a huge surprise to you that when we take the acceleration, we are just going to be taking another derivative. Position function is feet, velocity is feet per second, acceleration is feet per second. So it's a second derivative, or it's going to be our change in velocity over time. But let's repeat what we have going here with our velocity and position function models. So we have a time t, and we're usually given that position function, and I know in physics you call that x of t, same thing. And we're going to have our velocity function, which we're going to call v of t, and now we're going to introduce an acceleration function that we call a of t. So a little review. Remember that the velocity is change in position over time, which we'll call delta s over delta t, or, again, physics, this looks more familiar to you, but this is kind of what we're using. And that's a rate of change. It's the change in position over time. And it's the limit, remember, when we're doing instantaneous rate of change, we're this is average rate of change on that secant line, which we've talked a lot. When we're doing instantaneous rate of change, we're pushing that secant down and down and down, closer and closer, till it lands on the tangent, which basically we were taking that limit as the change in time approached zero, which is why we got that derivative, if you think of the definition of derivative. So we were saying that it's the derivative of your position function. And the way we write that is we say our velocity is the first derivative of position. And we've been working with that quite a bit. You've had those S of t models where it was negative 16t squared plus 16t, and maybe the building was 100 feet tall. And we said to find that instantaneous velocity, you take the derivative. And we would say it was negative 32t plus 16. And to find the instantaneous velocity at maybe 2 seconds, we just go plug it in. And we've worked with that already. Well, now we're going to introduce acceleration. Acceleration is the change in velocity over time. And sometimes we'll write that delta v, delta t. But really, calculus-wise, this is more the physics model, but calculus-wise, what you're doing is you're taking the limit of the change in velocity over change in time as that time approaches zero. So every time we're doing that, we've got another derivative. And this time it's the derivative of the velocity. So we would write this. My acceleration function at any time t, instantaneous acceleration, how fast am I speeding up over time right now, is the first derivative of velocity. Well, remember, velocity is the derivative of position. So sometimes we'll say that's the second derivative of position. What would be kind of helpful is if you list them in order, and you say S of t, and then V of t, and then A of t. And each of these adds a per. Like if we're in meters per second, this would be done in meters per second, and then this is meters per second, or you would write that meters per second squared. And every time you move down the line, you take a derivative. Let's move on down here. And this one we've talked about. Your speed is your absolute value of your velocity. So if you get your velocity of, say, negative 100 meters per second, then your speed is 100 meters per second. Remember, velocity is a vector giving direction. Speed is just quantitative. How fast are you going? So this next thing down here on the bottom is pretty important. It's popped up on a couple of the AP questions. And it'll ask you when the speed is increasing. Now, intuitively, when you're going, this is used a lot in what's called particle motion, where a particle is moving like left or right, or sometimes they'll say along the x-axis. And they say that the speed is increasing when both your acceleration and velocity have the same sign. So really what that means is they are either both positive or both negative. When you have one of each, they're kind of working at counter purposes, and they slow you down overall. This one's easy to kind of get a visual for, because obviously if I'm moving this direction, velocity being positive and my acceleration is speeding, I'm obviously going to be speeding up, or my speed will be increasing. I'm accelerating in a positive direction and the velocity is positive. It's a little weird thinking of it going in the other direction, but what you might want to think of is like a car gunning it in reverse. And some people think that negative acceleration means you're decelerating. That's really not what it means. I'm going to give you a numerical model just so you can kind of see it. Suppose you have like 1 second in to something, I don't know, particle motion or a car or whatever, and your velocity is -10. And let's say miles per hour, because I think we get a better conceptual when it's like in speeds with a car. And so keep in mind the speed here is 10. And then suppose at 3 seconds, I'm -15 miles per hour. My speed has increased. Obviously, you can see it. It's gone from 10 miles per hour to 15 miles per hour. Both the velocity is negative, as you can see, and watch when I calculate my acceleration. Your acceleration is change in velocity over change in time. So I'm right here, and I used to be there over my change in time. And you'll notice what I end up with is a negative acceleration, even though my speed has actually increased. And a lot of people just kind of memorize, well, 2 positives make a positive, 2 negatives make a positive. And that's true, but it's kind of good to have a mathematical idea of why that's working. So let's go to the next page, and I'm going to probably have to do this in 2 videos. This is a really good problem right here, and I'm not sure I'll get through all of it, but I'm going to do my best. So this is the position of a particle traveling along the x-axis. So it's basically something going left-right. And we're in seconds and we're in meters, and they've given me my position function. It says, when is the particle at rest? Well, the particle's at rest when it's not moving, or when the velocity is equal to 0. So whenever they ask you when it's at rest, you need to set the velocity equal to 0. Well, I need my velocity function. Remember, velocity is the first derivative of position. So let's go take that. We use our power rule, 3t squared. Then I'm going to have a minus 18t and a plus 15. And the derivative of my constant is 0. Now I'm looking for when it's at rest. So I'm going to set that velocity equal to 0. And you can probably see, I hate t's. And now you're going to probably be able to see what's going to happen here. I'm going to factor 3 out, giving me t squared minus 6t plus 5. I'm going to factor the remaining quadratic into t minus 5 and t minus 1. And what this means is I have 2 times. At 5 seconds and 1 second is when the particle is at rest or not moving, or has a velocity of 0. So that's part A. Now we'll go do part B. When is the velocity? What is the velocity? This is instantaneous velocity at t equals 4 seconds. Well, what you're looking for then is v of 4. And I already wrote your velocity function on there. It was 3 times t minus 5. It's actually easy to have it in this factored form, so I'm going to leave it. And I'm trying to figure at 4. And you could have plugged it in before the factored version too. It won't matter. You'll get the exact same answer. And when you plug that in, you're going to get a 3 times a -1 times a 3 for a -9, appropriate label, meters per second, which basically tells me it's moving to the left at a speed of 9 meters per second. I'm going to stop this now and restart another video, so there'll be 2 of them. This is part 1.